Hello everyone, my name is Dimitri Levitt. I'm the National Development Manager for Automation, Control and Industrial IoT for HYTALKS Australia. And thank you for joining me on this webinar. I hope everyone is practicing good social distancing and self-isolation techniques here. So we're, to try to keep people entertained and to educate during this interesting times. We wanted to present you with my webinar on the Australian market range of pressure sensors that we here at HYTALKS Australia have, and wanted to go over each particular sensor and some of the features they have, and we'll also discuss IO-Link. And if you have any questions, please write them down, and then we'll address them at the end of the webinar. So today, in the topics for today, we're going to discuss the sensor output types, the switching that are available within a sensor. We'll also discuss switching contact types, normally open, normally closed. I will go into IO-Link and some of the really cool features that are within IO-Link, and we'll also now go over the pressure sensors that we have. And the goal of the webinar is to simplify the pressure sensor selection process for you as the customer. And so when you give us a call or you're doing an application and need something in a hurry, the goal is to have these sensors on the shelf for you so we can deliver them in a fast manner. So now let's go over some of the output types that are available in our sensors within the HYTALKS range of pressure sensors, and we generally have this available within all of our sensor types. So let's start from the top. We have the analog outputs, which are 4 to 20 milliamps, 0 to 20 milliamps, 0 to 10 volts, and these are all common analog output styles. And on the left-hand side, you can sort of see the wiring diagram and some more technical specifications on the right-hand side. We also have switched or digital output style sensors, which are relay, which come in two types: relay, which is normally open or normally closed, and also transistor style outputs, PN, NPN, and they're also available in a normally open and normally closed. And we also have, on top of the analog and digital output styles, we also have smart sensors, or sensors that have a protocol output or a communication interface. For example, or a digital communication interface, something is like IO-Link, HART, CAN, Modbus, serial. And in particular, today we're going to concentrate on these output styles, which is going to be 4 to 20 milliamps, transistor with a PNP output, and IO-Link output sensors. And this is what I've considered as the Australian market range of sensors. So let's start first off with an analog 4 to 20 milliamp output style sensor. So this is the most common sensor available, most common like output style of the sensor available, and it's really commonly used in the industry. They generally come as a 2-wire sensor, as you can see in the middle of the page, where it says HYTALKS model code A. You can see the sensor, the HDA 7446-A, and you can see two lines where it's has a 1 and a 3. So that's the general resemblance of a 2-wire sensor. And the sensors generally follow a linear curve on the output. And I'll go over how a sensor converts a real world or a real physical property to an analog output soon. And some of the advantages of a 4 to 20 milliamp sensor compared to a 0 to 10 volt sensor is, current or a milliamp output is better over long distances, and it's not susceptible to voltage losses or voltage or electrical background noise as a 0 to 10 volt sensor. And one interesting part is, since the 0 bar, or the zero, or the starting point of the sensor output is 4 milliamps, so we can detect a broken wire on the sensor if the PLC reads 0 milliamps, for example, something that you wouldn't be able to do on a 0 to 10 volt sensor or a 0 to 20 milliamp sensor, because if there's a broken wire, it's still giving a potentially a valid reading from the sensor would output. So 4 to 20 milliamp sensor has that particular advantage if you for just for fault finding purposes. Another common output is the analog 0 to 10 volts, and this is also really commonly used around the industry, and comes in variants like 0 to 5 volts, 0.5 to 4.5 volts. It really depends on your application or what's required. So, this sensor is generally a 3-wire sensor, and so it does require a bit more wiring, but it's just really depends on your application. So, as opposed to the 4 to 20 milliamp or a current output sensor, this is more susceptible to electrical noise. So you need to provide suitable cabling and shielding and whatnot. So now I wanted to go over what we call like a switch contact. So this is what we call a normally open or a normally closed contact of a sensor. So this is different to PNP and NPN, and this style of output is available on sensors or pressure switches that have a digital output, and it's also available with a sensor that has a relay output. So normally open, as you on the left hand side, you can see that the normally open, generally dubbed NO, it's a contact that closes when a pressure setting is reached. So in this case, we're looking at pressure, and the contact will close. So when it closes, the voltage passes through, and it'll go to your system below, to your system. And normally closed contact works the opposite way to a normally open. So NC means normally closed, so the contact opens when the pressure setting is reached. So currently when the pressure setting isn't reached, voltage is being passed through in your control system, so that opens. And then you lose the signal, and your PLC will lose that voltage signal. So this is part of a switch contact output for a digital style sensor. And now if we go to the switch output, this is either a PNP or a NPN sensor. So I'll go over just a very high level of this particular output. So this is different to a relay output, and generally PNP or NPN sensors can switch a lot faster than a relay output, and they generally have a life cycle which is a lot higher. So in the millions of cycles, as opposed to relay output, which could be in the hundreds of thousands of cycle or event triggers. The interesting thing to note here is the voltage that you're supplying the sensor. So you can see the plus VDC is the voltage that you'll get coming out of the sensor, out of the output. So it's very important to know. So as opposed to a relay output, you could have a sensor that is being powered by a separate voltage supply, and then you can put another voltage supply through the relay. But PNP and NPN uses the supply voltage that you've provided to it. So it's generally used to trigger an on-off signal. If you really want to know more about PNP and NPN, it's the way that the transistor is designed. So you can please feel free to Google it, and it's quite low level electronics. So could be quite interesting if you're really interested in that level. So. And generally, these styles of outputs, like a PNP or an NPN, will be used to power on a relay, or it'll be used to connect to a PLC. So this is quite interesting. So this is what I'm going to go through here is how a sensor or an analog sensor measures a real world physical property and transmits that value to a PLC. So it's quite interesting from like what's like the smarts or the technology that are inbuilt into the sensor. So on the left hand side, you can see the fluid of like your pressure fluid or your hydraulic fluid or water fluid or whatever it may be is coming into the sensor through the orifice, and it's pushing up against the cell. So what happens on that cell, there's a Wheatstone bridge that measures the deflection, or so when the pressure builds up, the cell deflects, like micromillimeter. So you can't even see it, the eye can't see it, but on the cell there is a Wheatstone bridge, and the Wheatstone bridge is an array of resistors, and when the cell deforms, the resistance value changes. So then that resistance value, when that value changes, it goes through an amplifier, which is the triangle looking thing after the Wheatstone bridge, which is the 4 resistors with the P on the left hand side. So then it goes through the amplifier into an analog to digital converter, And then from that analog to digital converter, it goes into a microprocessor. So we amplify the signal so we can convert it to something that a microprocessor can read. And the reason we go through a microprocessor is because we want to apply temperature compensation and we want to linearize that signal to provide a best line of best fit, or the most accurate representation from what the real physical property is to what your PLC will see. And we do temperature compensation because obviously temperature affects metal, and the higher the temperature, the metal deforms. And same if the liquid is cold, for example, the same pressure could give you a different reading on the Wheatstone bridge. So we need to do that compensation, and we need that lookup tables and stuff. So that's done on the microprocessor, or it's what we call an ASIC, which is an application-specific integrated circuit. So now we've converted the real world value, or the real physical property, into the microprocessor of the sensor. Now so we've gone from analog to digital, which is the real world physical property, into digital, into the microprocessor. So now we have to convert it back into analog to send it to a PLC. And we send a signal via cable or shielded cable, and we can use one of the analog values, for example, a 0 to 10 volt or a 4 to 20 milliamp output. And then on that cable, it runs to a PLC, and into the PLC, we have to convert it back again from an analog to a digital value, something that the PLC program can understand, or something that the microprocessor in the PLC can understand and read, and you can write logic based on it. So, and the interesting thing is, if you had a sensor that didn't output an analog value, if it only had a switch output, instead of doing a digital to analog conversion, you'd be doing a digital to a switched output, which would be just an on-off instead of an analog value. So, but the interesting thing here is if you count how many times we've done a signal conversion. We've gone from analog to digital, which is the pressure in the fluid, going to digital to convert into a microprocessor. Now we're going back from digital to analog to send the analog signal via a cable, which you may have losses on the cable, and accuracies and you may be susceptible to noise and things like that. And now we're converting it back from analog to digital so a PLC can read. So that's 3 conversions that we've gone through. And every time we convert a value, we lose the representation of what the actual physical, what the physical property was, or the physical measurement was. So you may experience inaccuracies. And a lot of times when you have a sensor that may have a display and it may show 35.3 bar, but in the PLC it may show 35.2 bar or 35.4 bar, for example, after you've done the scale, after you've transmitted that value to the PLC. That's because of the analog to digital conversions. When you've gone from the sensor back to the PLC, you may have losses and it may not be as accurate. And the accuracy that the PLC sees depends on the quality of the analog input card that you may have, again, things like that. So you may need a higher bit resolution input card. So, and there's all these things play a part in how the PLC can read this analog signal. The reason why I'm showing this is because I want to show you how it looks in a smart sensor, or in particular in our case, a sensor that has IO-Link. So if IO-Link, as mentioned before, is a smart protocol, I'll go a bit more into IO-Link, but it's a type of output from the sensor. So it's a digital communication output of the sensor. So we're no longer using analog output to transmit the value. But so you can have a look in terms of how the sensor reads the real world value. It's the same. It goes through the pressure port, the cell, the Wheatstone bridge, the amplifier. We still need to convert the analog to digital to go into the microprocessor. We still apply temperature compensation and linearization to do that. So all that is the same, but the last part is the way we transmit that information to the PLC. We're using a communication chip or an IO-Link protocol to send that signal to the PLC, but that'll go through what we call an IO-Link master, for example, and I'll go into a bit more about that. But the main interesting point here is we've only done one signal conversion from analog to digital. We've converted a real-world property once to transmit it now to the PLC. So this means that we're going to see the closest resemblance to the real physical property, or to the actual pressure, or to the temperature that you may see. So it's a really interesting point from that. So you're never going to have that inaccuracies of signal losses or anything like that. So also very important to note is IO-Link is a open specification and open protocol. So it is not HYTALKS specific, and it is vendor, and there's hundreds of vendors out there that produce IO-Link sensors. So it's not a proprietary protocol. It's just an open standard. So, and as you can see, an IO-Link master is what's used to connect to the PLC. So you can see just how this goes into the PLC. We'll go through. We have an IO-Link sensor. We connect that sensor to an IO-Link master, and the IO-Link master is what you connect a number of IO-Link sensors to. So you can have, on this particular example, there are 8 IO-Link 8 IO-Link sensors can be connected to this particular IO-Link master, and this IO-Link master now talks or communicates via field bus, either Profinet, Modbus TCP, Ethernet IP, EtherCAT, OPC UA, and etc. So these are all common protocols that the PLC, that a PLC or a SCADA or a HMI can actually communicate, and can actually extract this data from the sensor, and then you use that field bus to connect to the PLC. So the PLC doesn't talk to the sensor directly; it goes via an IO-Link master. And you can also get IO-Link masters that are look like a analog input card on the PLC, and all it is converting the IO-Link signal to the PLC. So, but the main thing is you've only done the conversion once. Now, the IO-Link summary is just to summarize, it's a digital communication to and from the sensor. So you can actually write to and read from the sensor a lot of values, and I'll explain some of the values that can be read on one of our new smart sensors, and it's really quite cool the amount of data you can extract from an IO-Link sensor. So I'd generally recommend using this for applications where you have a stable 24-volt power supply. There is a standard where the voltage, if the voltage drop, like the standard of IO-Link is it's a 24-volt switched signal, so it's a really high frequency switched signal of the 24 of the sensor that actually does that transmission. And it's done on one cable. As you can see on the right-hand side, you can see the pin connection of an IO-Link sensor that's connected via an M12 connection. You can see the C/Q, and you can see that it's using the same output as it would for the PNP output of the sensor. It's actually using that as the IO-Link communication. So that's very important to note. And in some cases, you'll generally have to have a look at that on the data sheet of the sensor. You can use an IO-Link sensor as a normal sensor or as a IO-Link sensor. So the sensor also has processor functions on it, because we do have a microprocessor on it, and it can do some extra smart capabilities, and I'll explain that. It generally uses an M12 connector, so some sensors do come with different style of connectors. So, and as I said before, you need to have a look as, can an IO-Link sensor operate as a normal sensor? So this is an extract from the manual of our one of our smart sensors, and you can see here 6.1 SIO mode, which is a standard input output mode. So when the sensor powers up, it's running as a normal sensor unless the IO-Link master tells it to run as an IO-Link sensor. So now I'd like to bring you to our Australian market range of pressure sensors. So this is the range of sensors that we will carry. We have a huge and extensive range of pressure sensors, but to simplify and narrow down, to make it easier for our customers to detect or to select some sensors, this is the range that we will generally be keeping in stock, and I'll go over them one by one. So you can see This HDA 7446 is just a standard 4 to 20 milliamp sensor. Then we have an EDS 3400, which is an IO-Link pressure switch / transmitter. So this sensor can operate as a IO-Link sensor, as a digital output PNP NPN, or as a digital output PNP sensor, not as NPN, but it can also operate as a transmitter, 4 to 20 or 0 to 10 volts. So it's quite a versatile sensor. We have the EDS 8020 IO-Link pressure switch, which has two digital outputs, but can also operate as an IO-Link sensor. And we have the EDS 8000 pressure switch with a display and has 2 digital outputs. And then the one sensor I want to go through, which is at the moment not part of our standard stock range, but it's quite an interesting and unique sensor for the market and has a lot of functionality. And that's the HPT 1400S, which is our smart IO-Link sensor. So I'll go over, so now I'll introduce you to our HDA 7446. So this is our stock standard 4 to 20 milliamp sensor. If you need an analog sensor with a varying pressure range or something like that, this is the sensor for you. So if you're trying to control pressure in a pump or a power unit, or monitor pressure in the water line or something like that, this is generally the stock standard. This would be the sensor to go for. It's quite very, very industry standard. It has a 1/4 inch connection, analog output 4 to 20, but it also has a 0 to 10 volt output. At the moment, we will have some options of the 0 to 10 volt in stock, and we will expand that as required. But at the moment, the 4 to 20 is generally the much more commonly used output style, and we're going to carry it with the 1/4 inch BSP. If you do need a sensor, if you do have another process connection, the best is like Reese Plumbing or something. They sell connections, fittings and things like that. So you can see the pin connections, how pins 1 and 3. Pin 1 is your power supply, and pin 3 is your analog output. So just a quick summary on the sensor. This is it's a high robust, thin film strain gauge sensor, and it is designed for harsh environments as well. So it's comes from 10 bar up to 1,000 bar. So yeah. And we do have other output signals available. The next sensor is the EDS 3400, which is the IO-Link sensor, which is a pressure switch plus a pressure transmitter. This is a sensor that is a bit more complex because it can do a lot of things for you. If you have a look on the left-hand side, you can see that this has a number of switching mode outputs. It has on-off outputs, and also has a window function. And the window function is where the output of the sensor is on. If you have set up the sensor, for example, to be on between 10 bar and 50 bar, that means that the output will be on between 10 and 50 bar. For example, that's what a window function is. Or you can run that as a normal hysteresis style output, where your set point is 50 bar and your reset point is 10 bar, where the sensor turns on at 50 bar and turns off at 10 bar, so the switched output. And you can also program delays onto this sensor. So if you have a pump that may be going on or that the pressure may be fluctuating, but you don't want the light or like a warning light to turn on and off when it's not required. So you can put a delay onto the sensor, and up to 99 seconds. But the interesting thing is this sensor can do 4 to 20 milliamps and 0 to 10 volt or 0 to 10 volt output. So you can use this sensor with a switched output, like a PNP output, and also as an analog output at 4 to 20 or 0 to 10 volts. So it's quite a versatile sensor. And to make things a bit more confusing, it also has IO-Link. So it's quite a versatile sensor. So this would be a really good sensor. If you have if you're distributing these sensors, you can have this on the shelf. It could be if you have running service technicians, this is a good sensor to have in their in the service vehicle, because it can do a lot of things for you. It's quite flexible. It's customizable via the screen. So yeah, and you can see some of the highlights there on the right hand side. So 2 outputs and PNP, and it can be either normally open or normally closed, configurable via the screen. And yeah, and what's it called? and also has a 1/4" BSP and an M12 connection. So the next sensor is the EDS 820, and so this is a IO-Link pressure switch. So also, as you can see on the left-hand side, on the bottom left-hand side, you can see that it runs, you can see Q1 and Q2. So it can also operate as a standard PNP sensor, and has works in hysteresis mode or window mode, as you can see. So it can be customizable, but it can also run as an IO-Link sensor, and you can connect it to an IO-Link master. And if you do that, you actually don't just get the on-off or the switch values of the sensor. You can actually read the pressure value from the sensor as well. So you get the analog value via IO-Link in your PLC. So sorry to confuse people, but it's also quite a versatile sensor, and you can program this sensor using our HMG 4000 tool, or a handheld programming tool, a HPG P1, or a computer or a PC-based programming tool. So it comes in various different pressure ranges as well. Again, 1/4" BSP and M12. So as you can see here, like the 1/4" BSP is quite a common, what's it called, style connection. Then we also have now the EDS 8000 pressure switch, and this is not an IO-Link sensor. This is just a sensor that has two switching outputs, which are PNP. But you can get this as an NPN version, but it needs to be ordered specifically. But instead of programming this device via another tool, it has a little display on board and has two programming buttons. So you can actually set this up with no other tools required, and using the buttons on board. So you can set up the normally open, normally closed functions. You can display the pressure in either bar, PSI, or megapascal. So, and it's quite a common, it's quite a versatile sensor. So also another good option to potentially have, as a get out of jail sensor that can be can be programmed if you need something urgently and things like that. So yeah, it's quite a nice little versatile sensor. And now I want to bring you to our HPT 1400S. This is our smart IO-Link sensor, and it's so it also can operate as a PNP output sensor. But to get the most value out of this sensor is you use this sensor with an IO-Link master communicating to a PLC or a SCADA or a HMI. This sensor is quite unique because it does data logging on board, and I'll show you a bit more what it actually logs. But it can also log, maximum and minimum values that it sees, and a few other things, and I'll explain a bit more into that. But it's our smallest sensor as well. It's quite small physically, and we'll go over a bit more what it can do. So one of the things that it can log is so when you're connecting this via IO-Link, obviously you can see the current values. You can see, so this is what I'm showing you now is a data sheet, or the electronic data sheet for IO-Link sensors, which is called an IODD file. And there's a one website that keeps all of the IODD files for every single IO-Link sensor in the world. And this is a description of the data that you can receive from the sensor. So you can have a look here. It's like the pressure value. You can see that you can read the current value of pressure within 2 decimal places. So an interesting thing is you're reading this as the actual bar value of the pressure range. But also it'll also store the min or the maximum value, the pressure that it actually sees. And you can reset the value. So for warranty purposes or application purposes, you want to see what has been the maximum value or the maximum pressure that this sensor has seen or your process has seen in the last 24 hours, for example. And you would read this max value, and the PLC can actually read this value, and then you can reset that value to go back to 0, and then you can keep reading that value. You can also, because as I explained earlier, we do temperature compensation on the sensor for linearization. And since we do temperature compensation, to do that, we need a temperature sensor. And when that temperature sensor sits inside the cell on the electronics part, so you can actually measure the temperature and give a good representation of what the fluid is, but it's not, I wouldn't use it as a temperature controlling device, but you can use it to actually see if the sensor is going above temperature itself, and you can record that value, and maybe you can calibrate the temperature value of the sensor to your process, and you may actually be able to use it as a controllable something to control your process. But you can also reset this value min and max. But the more interesting thing is you can see lifetime pressure. So this is the values that cannot be reset and never get reset, and these are non-volatile. So all these are non-volatile, and they won't be reset, apart from the top ones where you can see it says can be manually reset by a command. But these lifetime pressures don't get reset. So you can monitor for the life of the sensor to see what has been the maximum, the minimum, and the average value that this sensor has ever seen in its life. But also what's cool, you can actually record how many times the sensor has gone above its nominal range, which will be the pressure rating specified on the data sheet, or the measuring range specified on the data sheet, and also has gone under that. So you can actually see how many times you've had pressure spikes and things like that. So you can actually read that value in your PLC. And then you can also, and part of the sensor in terms of the statistics that it does, it logs over its lifetime how much time in seconds it spends within a certain percentage of its pressure range. So as you can see here, this sensor it's broken down from less than 0 bar to greater than 45 bar, and for every second that the sensor spends within that certain amount of time in that pressure range, it actually logs, and it will tell you how many seconds it actually spends in that pressure range. And if you're wondering, well, you must need a lot of data to record this, must need a lot of memory on the sensor to actually record all these values. Well, actually you don't, because 32 bits can store a couple of million seconds, and a couple of million seconds equates to a couple of 100 years. So if this, if we're still around in a couple of 100 years and then we run out of memory, then we're doing pretty well. So so you can see that. So you might be able to use this in an application where you've designed a system that needs to operate, and say you have design a system that needs to operate at, say, 80 bar, but you can't, and you've put a 250 bar sensor in there, for example, but you're noticing that the system is operating at 130, 160 bar majority of its life. Maybe you can use that information to redesign the system to see how to, or why is it operating at that particular range. So it can give you some data as the performance, or or if it's operating constantly at above its design pressure, is it going to reduce the lifetime of this of the system that you've designed. So, and the other interesting thing with IO-Link sensors, and this one in particular, it gives you events, or what we call warning and error information that your PLC can read. So a lot of the time you may get a call like, oh, the sensor's not working, or the process isn't working in a plant. But if you have a sensor like this, you could actually, if the fault was to do with the sensor, you'd actually know what the issue is with the sensor before you would even have to go to the sensor. For example, we can tell if the sensor is in an environment where it's too hot, or if it's too cold, or for example, if the sensor's gone above range. But in particular, it also tells you, it monitors itself, and it tells you there's a device hardware fault, and it tells you how to fix that. You exchange the device. So how good would it be if you received an email from your SCADA system saying, hey, there's an error, there's an issue with me, or like for example, this sensor is emailing you via your system saying I need to be exchanged because it has received that particular error code. So that could be quite interesting from like a industry 4 point of view, or a predictive maintenance point of view, and things like that. So it's kind of a cool sensor. So thanks for that. I hope you guys are still with me, and that made sense to everyone. And please practice social distancing. Not sure if this joke will land, but since the self-isolation laws, self-isolation has been encouraged, the software development efficiency in our software development department has skyrocketed. So I hope that joke lands. I can't read your expressions, but thank you very much for joining me. Thank you.